Let's talk about the concept of maintenance and loading doses. Let's use an example of warfarin. Warfarin is a drug that requires very close monitoring of therapeutic levels. Here's a patient who takes 1 milligram of warfarin. Clearly, 1 milligram is not going to cut it for this patient, so we need to give him more every day. If he takes 1 milligram every single day for 9 days, eventually we will get to the effective concentration that we want. But that seems like a long time. Why don't we give him a whole bunch of medication at first, or what we call a loading dose? So here's an example of a patient who took 10 milligrams on day 1. You can see the concentration really climbs, and then after that we give him 1 milligram a day. That's the concept of a loading dose. So in warfarin, we use loading doses all the time. The loading dose can be calculated. It is a formula using bioavailability, the target concentration, and the volume of distribution. So it's VD times the concentration divided by the bioavailability. Now the dosing rate, or how often we give the medication, is the clearance times the desired plasma concentration, once again divided by bioavailability. Let's use bioavailability and volume of distribution to calculate dosing. Here's a case study of a 15-year-old woman who has pneumonia. She requires an antibiotic called Supercillin, which of course doesn't exist. It has a volume of distribution of 31 liters and has an oral bioavailability of about 55%. The required plasma concentration is 55 micrograms per milliliter. What is the loading dose? Well, let's do the calculations together. We know that the loading dose is the volume of distribution multiplied by the concentration and divided by bioavailability. Let's plug in the numbers. So you can see here that there's 31 liters times 55 mics per mil divided by 55%. That's 31,000 milliliters, right? So we're going to convert that. It's multiplied by 55 mics per mil. And the percentage number, we're going to substitute 55% in the denominator with 100 over 55. The loading dose is therefore 31,000 times 55 times 100 divided by 55, and canceling out the 55s and canceling out the milliliters, you get 3.1 million micrograms, or 31 grams. This 15-year-old girl with pneumonia is getting worse. The Supercillin will be needed to be given intravenously. Supercillin, VD, has of 31 liters, bioavailability 55%, intravenous bioavailability of 99%, and a required plasma concentration of 55 mics per mil. The clearance is 6 mils per minute. What's the dosing regimen of the drug? The dosing rate is the clearance times the concentration divided by bioavailability. The dosing rate is 6 mils per minute times 55 mics per mil divided by 99%. We do the substitution, we cancel out the milliliters, and we get 333 micrograms per minute. And if we multiply that into hours, we get 20 milligrams per hour. Let's do a study on loading and maintenance dosing. A 66-year-old woman had a cardiac arrhythmia which responded to lidocaine. The ideal serum concentration is 3 mics per mil. The volume of distribution is 75 liters. The clearance is 600 mils per minute, and the half-life is 1.5 hours. The bioavailability is 60%. What's the loading dose, and what's the ideal infusion rate? Okay. So loading dose, once again, 75 liters is the volume of distribution, the target concentration is 3, and the bioavailability is 60%. So we plug that into our equation, and we do the math, and we end up with 375 milligrams as your loading dose. The infusion rate is going to be your serum concentration multiplied by your clearance divided by bioavailability. We're going to give an infusion rate of 3 micrograms per mil times 600 mils per minute times 100 over 60, which gives us 3,000 micrograms per minute, or 3 milligrams per minute, or if we convert it into hours, it's 10.8 grams or 10 grams an hour.